So, hello and welcome to this NPTL TS session on heat transfer course. And today is the week 13. So, today we will be, I think, all the week's course content are completed. So, in this week, we will be doing some questions from different questions from throughout the courses so that it will be a final touch up on all the contents that you have studied in the entire lecture series. Okay, so we'll take up questions from different sections like conduction, convection, radiation. From everywhere we will be taking up some questions. and try to solve them. Okay. So let us start by first question. It is given that temperature of a flame in a furnace is 1900 Kelvin. Okay. So we have the flame of a furnace which is at 1900 Kelvin. So find the monochromatic energy emission at 1 micron per meter square. So this is the first bit. So you have to find the monochromatic energy emission. Monochromatic energy emission, okay, at 1 micron per meter square. Okay, so this is the first bit. So you can give it a try. I think you can directly use the formula to get the solution. So let me write all the bits first. So the second bit is you have to find the maximum lambda, that is lambda max. Then you have to find out the monochromatic energy emission at lambda max, that is monochromatic energy emission at lambda max and at 1900 Kelvin. Okay. Then you have to calculate what is the ratio of EB lambda, okay, by EB lambda max. So this is from above you can calculate. And the total energy that is emitted per meter square is total energy emitted per meter square. So you can give it a try and then we can discuss the solution. Okay, so let us see the solution. So the first part is find the monochromatic energy emission at 1 micron per meter square. So if you remember how we calculate the monochromatic energy emission, so it is E B lambda, that is equal to C1, that is a constant, lambda to the power of minus 5, entire thing divided by, we have exponential of C1 by C2 by lambda t minus 1. So C1 and C2 are constants. So, and lambda you can see here. So you just have to substitute this. So let me do. So this is 3.74 times of 10 to the power of minus 16. And then lambda is given to be 1 micron, that is 10 to the power of minus 6 meters. So 10 to the power of minus 6 to the power of minus 5, and this divided by, we have exponential of C2, that is 0.14389 and divided by lambda is 10 to the power of minus 6 times of T, temperature is 1900, and this minus 1. So if you simplify this, you will be getting around 1 1.918 or 92, let's say, times of 10 to the power of 11. Okay, watt per meter square meters. Now the second part is you have to calculate lambda max. For lambda max, you can calculate it from the Wien's displacement law or Wien's law. That is lambda max into T is equal to constant. That is lambda max times of the T is equal to constant 2900. So we can write 2900 divided by T. Okay. So this is equal to 2900 divided by 1900. So this will be equal to 1.53 microns. Or we can write 1.53 times of 10 to the power of minus 6 meters. Now the next question is, what is the monochromatic energy emission at lambda max and at 1900 Kelvin? So for that also we can use the above expression for EBW, but it will be lambda max. Okay. So we will be having EB lambda. We can write it as max, and this is equal to, we can use the same expression that we have here, but instead of the lambda we will be changing the lambda, right? So here additional terms will be coming. Let me do this. So here it will be 1.53 times of 10 to the minus 6, and here also 1.53 times of 10 to the power of minus 6. And if you do that, you will be getting 3.18. So let's say 3.2 times of 10 to the power of 11 watt per meter square meters. Okay. So the next you have to calculate is, what is the ratio of EB and EB lambda and EB lambda max. So this you can do very easily, I think, from the above 1 and 3. So we have EB lambda divided by EB lambda max. So this is equal to 1.92. So 10 to the power of 11, I am not writing 10 to the power 11 because it will be cancelled, divided by 3.2. So it will be around 0.6. And then you have, what is the total energy. So total energy, if you integrate this EB lambda, okay, for all values of lambda, you will be getting the total energy, and that is what we also know as the common expression for the Stephen Boltzmann law. Okay, that is E B for all values of lambda, and that is equal to nothing but sigma times of T to the power of 4. So this is equal to, we have 5.67 times of 10 to the power of minus 8, and this is T, that is 1900 Kelvin. So we have 1900 to the power of 4. So if you do that, you will be getting, this is equal to 0.74 times of 10 to the power of 6 watt per meter square. Okay. Now let's move on to the next question. Consider this. Let me draw the figure. So consider that there is, say, oxygen here. Okay. Say oxygen. Say liquid oxygen, which has a boiling temperature of minus 182. So we have liquid oxygen, okay, which has a boiling temperature, let's say TB, is equal to minus 182 degree Celsius, is to be stored in a spherical container of 30 centimeter diameter. So storage in spherical container which has a diameter of 30 centimeter. Now the system is insulated by an evacuated space between the inner space and the surrounding 45 centimeter inner diameter concentric sphere. Okay. So this part that we have, this is nothing but the evacuated space. Okay. And this has a inner diameter of 45 centimeters. So let me say, so we have insulated system. Let's say insulated, okay, by an evacuated space. By evacuated space which has a diameter of 45 centimeters. For both the spheres, the emissivity is 0.03. For both spheres, emissivity is equal to how much? 0.03. That means for, let's say, you have this, okay, and this, both of them, okay. So this also and this one also has the emissivity of 0.03. And the temperature of the outer sphere is 30 degree. So let me write temperature. This temperature is 30 degree Celsius. Estimate the rate of heat flow by radiation to the oxygen in the container. Okay, estimate the rate of heat transfer, let's say, by radiation to the oxygen in the container. Okay. So again, you can give it a try and then we can try to solve this question. So let us try to see the solution. So the outer temperature is at 30 degrees Celsius and inner temperature will be nothing but the boiling temperature of the liquid, that is minus 182 degree Celsius, right? So we can calculate Q is equal to, we have A1 sigma, we have T1 to the power of 4 minus T2 to the power of 4. Now divided by, we have to add all the resistive components. Okay. So the first will be obviously 1 minus epsilon 1 divided by epsilon 1. Then we have plus 1 divided by F12 plus, we have 1 minus 1 minus epsilon 2 divided by epsilon 2, but here we will be multiplying with the area ratio. So we will be having A1 by A2. Okay. Now, if you see for this inner sphere, all the radiation that will be coming out from the inner sphere, nothing will be intercepted by itself. So F1 to 2 will be 1, because there is nothing for 1 to be coming back to 1. Okay. Therefore, we can write, this implies we can write, so this we can substitute it directly here. Okay. And area ratio next is this one is done. So F1 to 2 is done, and left is area ratio, and epsilon 1 and epsilon 2 both are equal to 0.03. So we have to only just see what is A1 by A2, and that is nothing but 4 pi r square or pi d square. So pi will be cancelled out. So we can write d1 by d2 square. Okay. So we can simplify this expression. So this term will be going to 1. Okay. So here also we have 1 divided by epsilon 1 minus 1. So this term will be also will be 1 divided by epsilon 1 minus 1. We have here plus 1 plus this thing. And this also will be now d1 by d2 square. This will be d1 by d2 square. So 1 and 1 will be gone. And now we have to substitute the values. Okay. So this is equal to, so we have 5.67 times of 10 to the power of minus 8, and we have 4 pi r1 square, or pi d1 square we can write. So we can write here pi, and d1 is 30, so that is zero point 0.3. So we have 0.3 square, and then we have t1 by t2. Sorry, t1 to the power 4 minus t to the power 4. So that is nothing but uh, minus 182 plus 273 to the power of 4 minus. So this will be less than this. So, but that is okay. We can take the negative value of whatever will be coming. So that is not a problem. So 30 plus 273 to the power of 4. Okay. And now we have 1 by epsilon, that is 1 divided by 0.03, plus we have 1 minus epsilon again. So that is 1 minus 0.03 divided by 0.03 times of, this is d1 by d2. So we can write this as zero point 0.3 divided by 0.45 square. So this is equal to minus 2.72 watt. So here this negative sign means it should be from outside to inside. That's it. Okay. So negative sign implies the heat transfer is from outside to inside. Okay. Now let's move on to the next question. Consider that there is a engine oil at 150 degrees Celsius and is cooled at 80 degrees Celsius in a parallel flow heat exchanger. So let's say we have a engine oil which is at 150 degree Celsius and is cooled to 80 degrees Celsius. So this is cooled to 80 degree Celsius using a parallel flow heat exchanger using parallel flow heat exchanger. Okay, so this, let me do like this, and this is done by using water which is entering at 25 degree Celsius and leaving at 60 degree Celsius and leaving at 60 degree Celsius. So the first bit is estimate the heat exchanger effectiveness and the number of transfer units. Okay, so let us see. Now, engine oil is entering at 150 degrees Celsius and is cooled to 80 degrees Celsius, and water is leaving and entering and leaving at 25 and 60 degree Celsius. So we can do energy balance for the hot fluid and the cold fluid. Okay. So let's say that this is the hot fluid. Okay. Just give it a name. And this is the cold fluid. Okay. Now let's do the energy balance. So we have m m dot c. Okay. cpc times of tc2 minus tc1, right? And similarly, we can write m dot h times of cph times of th1 minus th2. So now if we take the ratio, that is, if I write m dot h times of, write m dot h times of cph, okay, divided by m dot c times of cpc. So this will be nothing but This will be equal to uh, TC2 minus TC1 divided by TH1 minus TH2. And that is equal to uh, 60 minus 25, right? So we have 60 minus 25, and this is 150 minus 80. So we have 150 minus 80. So this is equal to around 0.5. Now, first we have to calculate the heat exchanger effectiveness. Now, if you remember the effectiveness, the expression for effectiveness, let me write, which is nothing but this epsilon is equal to, you can write CH times of TH1 minus TH2 whole thing divided by C minimum times of TH1 minus TC1. Now, if you see these term, this ratio, this CPH by this thing, okay. Now you see that this C minimum, we have a ratio of 0.5. Okay. So this minimum, the C minimum is same as that of CPH because the ratio is 0.5. So this equals, we have TH1 minus TH2 divided by TH1 minus TC1. This equals, we have 150 minus 80 entire thing divided by, we have TH1 is 150 minus 60. sorry, 20, not 60, 25, right? 25. So this is equal to 0.56. Now, to calculate NTU, we can use this expression or this value of effectiveness. Okay. Now, in terms of this capacity ratio and the number of transfer units, we can write the expression for effectiveness for parallel flow heat exchanger. So we can write this epsilon effectiveness is equal to 1 minus exponential of minus times of NTU. We have 1 plus C, okay, plus divided by 1 plus C. So this implies we can write this is nothing but 0.56 and this is equal to, we have 1 minus exponential of minus times of NTU 1 plus C. Now what is C? Is this capacity ratio is nothing but this one, that is 0.5. Okay, and this divided by 1 plus 0.5. So you need to simplify this. This implies we will be getting exponential of, this is 1.5 minus 1.5 times of NTU, and this will be equal to 0.16. So if you do this, we will be getting NTU is equal to 1.221. Okay. Now there is another part to this question. Let me write it here. Let's say if the fluid flow rate and the inlet conditions remain unchanged. Okay. So fluid flow and inlet conditions remain unchanged. Then what will be the lowest temperature? Lowest temperature, what will be the lowest temperature to which the oil may be cooled? Hmm. May be cooled by increasing the length of the exchanger. By so again you can think about it. This is only a small part of this. Okay, so now let us see how to solve this part. So we have to increase the length of the exchanger. So the exit temperature, uh, we have to find the lowest temperature. So the exit temperature will be minimum uh, if like in the situation, and we have to increase the length of the exchanger. So when can we achieve that lowest temperature? Is when we increase the length of the exchanger to infinity. Correct. So in that case, what will happen? So you can take that this NTU term tends to infinity, because uh, we have this dimension term in the denominator, that is area or A. Okay, so when the length tends to infinity, in the numerator area, right? So when the length tends to infinity, this NTU term will go to infinity. So whatever expression that you had previously, this one, in this NTU term will be infinity. So we have 1 by exponential of infinity term, which is nothing but this will reduce down to 1 by 1 plus c, which is equal to 1 by 1 plus 0.5. So this is equal to 0.667. Now you can again obtain this is equal to nothing but we have TH1 minus TH2 divided by TH1 minus TC1. So this is equal to 150. We have 150. We have to find out this TH2. What is the minimum temperature we can cool it down? So TH2. And this is 150 minus 25. And obviously this is nothing but 0.667. So if you do this, you can obtain TH2 is equal to 66.62 degree Celsius. So now let's move on to the next question. Consider a hollow cylinder. So we have a hollow cylinder of inner radius as 3 centimeters. So let me write it as Ri Ri equal to 3 centimeters and 4.5 centimeter outer radius. So the inner and outer temperatures are maintained at, so that let me write Ti is 380 degree Celsius and T outer temperature is 360 degree Celsius. The thermal conductivity of the material of the cylinder only, okay, thermal conductivity K of the cylinder material is equal to 20 watt per meter degree Celsius. So calculate the temperature at the mid radius. So I think now you can clearly understand or picturize this. So you have to calculate in mid radius somewhere here. I think this is pretty much straightforward. So you can directly do this. Okay. But we'll make it little bit more complex. Let that there be some heat generation as well. And let this heat generation be at the rate of 5 times of 10 to the power of 6. Okay. So now you can try to solve this. So let's see. So with the expression for heat generation, the temperature distribution with heat generation was obtained to be T minus T1, and this is equal to Q by 2 times of K. The R1 square minus the radius R, plus we have T1 minus T2 minus Q by 4K, and we have R2 square minus R1 square. Then we have log of, or we can write ln, right? Ln R by R1, or divided by ln R1 by R2. So you can substitute the values. So this is nothing but 380 This is 20. This is 5 times of 10 to the power of 6. Okay. And this is 3 centimeters, so point 0.3, 0.03. And this is the mid radius. Mid radius you can calculate, that is 3 plus 4.5 divided by 2, that is 3.75 centimeters. Okay. So this will be nothing but 0.0375. This is again, we know this is 380. This is 360. This is 5 times of 10 to the power of 6. This is 20. And this one is 0.045. And this is 0.03. Similarly, R1 and R2 you know, and R and R1 values also you know. So if you substitute everything, you will be getting T is equal to 373.7 degree. Okay, let us do another question. Consider a stainless steel wire, okay, which has a thermal conductivity of 20 watt per meter degree Celsius, and has a resistance, resistivity of 70 micro ohm centimeters, and has a length of 2 meters and diameter of 2.5 mm. And it is submerged in a fluid at 50 degrees Celsius. And this stainless steel wire is submerged in a fluid at 50 degrees Celsius. An electric current of intensity, let's say, let me write, an electric current I, which is 300 amps, passes through this stainless steel wire. If the conductance at the wire surface Let me write it here. If the conductance at the wire surface is equal to 4 kilowatt per meter square degree Celsius, what is the steady state temperature at the center and at the surface of the wire? Okay, so let us see. So first, let us calculate the electrical resistance of the wire. So the resistance is equal to rho times of L by A, right? So this is nothing but 70 times of 10 to the power of minus 6. Length is 2 meters. This thing divided by, we have area is pi by 4. So this is 2.5 times of 10 to the power of minus 3 square. So this will be 0.285 ohm. Now the heat generated we can calculate, that is I square R. So heat generated I square R. So this is equal to 300 square times the resistance is 0.285. So this much watts. Now we have to calculate the volume of the wire, which is so this is a cylinder. So pi r square L or pi by 4 d square times of L. So that is pi by 4 and d is again 2.5 mm. So 2.5 times of 10 to the power minus 3 square times of 2. So this is 9.81 times of 10 to the power minus 6 meter cube. So you can calculate the heat generated per unit volume. It is the heat that is generated per unit volume, that you represent that as Q. Or we can write only Q. Okay, small q, and that is equal to 300 square times of 0.285 divided by 9.81 times of 10 to the power minus 6. So this is equal to 2.615 times of 10 to the power of 9 watt per meter cube. Okay, so you can now obtain the surface temperature of the wire. Okay, so the surface temperature of the wire is nothing but T ambient plus this is Q divided by 2 times of H times of the radius. So this is 50 plus heat generated per unit volume is 2.615 times of 10 to the power 9 whole thing divided by 2 times of H. So this is nothing but 4 times of 4 times of 1000, right? So we have 4 times of 1000 times of the radius. Now radius is how much? So this is 2.5 divided by 2. So 1.25 times of 10 to the power of minus 3. So if you do that, you will be getting 50 plus 408.59. So this is roughly is equal to 458.59 degree Celsius. Okay, so this is the surface temperature. And the next is to find the steady state temperature at the center. So that is also the maximum temperature. So you can write T max, which is nothing but the temperature at the center is equal to nothing but TA plus Q by 2H times of R plus we have Q by 2K times of R square. And this thing is nothing but TW, right? So this is nothing but TW. So we can write this to be equal to TW plus Q by 2K times of R square. So this is equal to 458.59 plus this is again 2.615 times of 10 to the power of 9 and this divided by 4 times of 20. And then again we have the radius that is 1.25 times of 10 to the power of minus 3 square. So this is nothing but 458.59 plus this, if you simplify, you will be getting 51.07. So this is equal to 510.66 degree Celsius. So I hope you understood this question. So today we will be solving this much only. So I think today is the last session. So everyone, you can practice more questions, and all the best for your exams. So all these videos are uploaded. You can go through them again in the YouTube. Uh, in YouTube, they are available, and also the link to all of these video lectures are available in the portal, the Swayam portal. So you can register, you can log in there, and then you can get the link to all of these videos. Okay. So practice more questions. So when you practice more questions, you will be getting ideas on how to solve this easily. And all the best for your upcoming exams and all the exams in heat transfer. Okay. All the best and thank you.